Due to technical difficulties, the quality of the following recording is not up to our usual standards. However, we are releasing this due to the importance of the material presented.
So I'm going to be talking about evolutionary fuzzing. Revolutionizing the field of gray box attack surface testing with evolutionary fuzzing. And if my little HP pointer thing works, it never works, then I'm going to use it to try. Yes? Okay, so I'm going to hit some quick goals, do some background, and talk about the actual system that I developed, talk about some initial benchmarking and initial results of the 4 main points of the talk. So at any point throughout, if you have questions, ask, there'll be time at the end. And maybe if you're all very tentative, I'll let you out like 10 minutes early for lunch or something. Good? Okay. Go. No? Alright, well, it's not going to work, so anyway. So the idea is to build a better fuzzer, right? That's the whole idea of the research that I'm doing. That's the point. We want to find bugs, new bugs. And I don't have any proof yet that this is the way to do it, the best way to do it. In fact, I talk at the end that depending on the domain you're looking at, makes a big difference in terms of which approach you've got to take. So, to my knowledge, this is the only evolutionary fuzzing tool that's been released publicly. Last year, you may have caught Hamilton, Sparks, and Cunningham talking about Sidewinder, but to my knowledge, they never released code. The same thing with Bigman and Cunningham have done some work, but didn't release code. And there's other fuzzers out there, plenty of them, that use debuggers to get exceptions and all that kind of stuff, but not giving feedback back to the fuzzer to dynamically create better test cases. So, yeah. Talk about software testing first as background. Just a quick. Basically, it's tough. That's the only point of the slide, is just to say that you can't really prove that software is secure. You can prove that there's bugs if you find bugs. And it takes a lot of your budget, it's really hard, yada, yada, yada. People are doing better at it, right? Microsoft's doing better at it than they were. So testing is really all we have to give confidence. How do I sound with this? Okay? Voice good? Okay? Good. Alright, stay with me. They say that the average person in a talk zones in and out every 30 seconds. So if I stop every once in a while and go like this, where were you thinking about just now? What were you thinking about? You were thinking about sex. You said, I know. Stop thinking about sex. Focus up here, alright? Every 30 seconds I might do that. So if I do, bear with me. Okay, so fuzzing isn't like the end-all be-all of testing. It just fits in. It's one little piece, right? And it's an important piece. And companies sort of are learning, like, how many people yesterday or today, raise your hand, had a speaker mention the word fuzzing? Speaker talked about fuzzing. Yeah, so quite a few, and that's good, right? So, this is a diagram I ripped off from Peter Olhart. He wrote in 2005 an article, I IEEE article called Violating Assumptions of Fuzzing, and it was pretty much like that. I changed it a little bit, but it's sort of like generate a test case, deliver it to the application. Did some problem happen? If it did, record it. If not, go out to the next test case, however you're doing, either dynamically generating or randomly or taking from predetermined test cases. So, the monitor might be CPU usage, it might be memory usage, it could be if it crashed, if it got a memory access violation, whatever. So, how many people had a speaker yesterday or today mention attack surface? Raise your hand. Quite a few, probably the same number of people that heard fuzzing, right? So attack surface and fuzzing, people I think are really finally, probably in the last year, they really get it. They know what these terms mean. They realize that the attack surface is not all the code, right? It's actually a fairly small subset, typically. So it could be a network interface, it could be when it reads in and parses files, it could be inter-process communication. That's part of the vulnerability analyst's job or the security tester's job to figure out what is the attack surface. And it's actually kind of a tough problem to figure out, like, if you know your code has, say, 1,000 functions, how many of those 1,000 functions can you touch from the attack surface? That's actually a topic in and of itself that probably deserves research. So go forth, do good things, mention me in your paper. Come back. Everybody's back, right? 30 seconds. So, what is evolutionary testing? It's kind of a fancy academic kind of sound. I like to use academic words, it makes me sound smart. So, genetic algorithms is basically a computer science search technique that's sort of inspired by biological, so it's sort of like survival of the fittest. These two files, these two sessions, whatever, they did better, they got more fitness, more code coverage is what I'm using in general, diversity as well. I'll talk about that in a second. So they get together and think about what you were thinking about. Now they made, right, and they produce children, and those children do better than the next generation. That's the idea. So, standard evolutionary testing, though, as it's defined in the academic world, is mostly, you need software. You need source code, basically, to do it. So here's the example. You see we have this example function. It takes 4 arguments, A, B, C, D, 4 integers. And in this example, the 4 ints are 10, 20, 30, and 40. And we're trying to get to where the synthesis target / target. That's where we're trying to generate test data that would take us to that point in the program. So the way we measure fitness is we basically say, okay, first is A greater than B? No. So we fall out of the branch, and there were 2 more branches left. So it's 2 branches plus what's 20 minus 10 is 10. So 2 branches plus the normalization of 10 would be the fitness in this case. And if fitness equals 0, then we found the target. I think it's kind of screwy that as things get more fit, it goes towards 0. So in mine, as things get more fit, it gets the number gets bigger, just because it makes more sense to me. But that's sort of the standard way. This slide, all this slide is trying to tell you is that basically there's people out there doing this, particularly in situations where the software is safety critical. And this is a great example, by the way. Some people tell me, oh, denial of service is kind of lame. I only like code execution. Well, I like code execution too. But guess what? If I'm on the iron lung and somebody denial of service is my iron lung, you know what I'm saying? Yeah. So that's a bad thing. So here's an evolutionary testing. Here's some problems that you may have in evolutionary testing. We're trying to look at the code snippet on the left and look at where we're trying to get to / target again. Anybody see what the problem there is? Who sees it? Who's got a tell me what the problem is here. Anybody know? Do we have any genetic algorithms people in the crowd? Are there any professors at a university that do this for like a living? GA? That's good. That's good. Yeah. Well, it's not that you'll never get to it. The problem is that we don't control that. So if flag, then target, but we control A and B, right? So the genetic algorithm doesn't really know how to deal with that because it doesn't control those inputs. Now, it's not too hard for the human to see, well, if you make A0 and B0, then the flag will be 1, and then we'll get to target. Right? You can see that by analyzing the code, and it's not too hard to extend that. And there's people working on it. I'll show that on the next slide. The work they're doing is called extended chain approach to evolutionary testing. The next problem, so by the way, if you're not a genetic algorithm guy, there's this notion called fitness landscape, and that basically means like you're trying to search for this, and you want a continuous function from where you are to that, so you're sort of hill climbing, right? And the flat means that when it sees if flag target, it doesn't know how to climb anymore. It just does, so it's basically random search. It might still get there actually, but it's random. It has to just start using random numbers for the inputs. It doesn't know how to search intelligently at that point. So it reverts to what they call random search. But even worse than flat spots in your fitness landscape are deceptive spots. Can anybody look at the code snippet on the right? Come back, 30 seconds, come back. Code snippet on the right, see where the target is. Anybody see what the problem there might be?
Double roll is never really 0. I mean, it's not valid unless the double is 0.
Well, okay, so if it's int or whatever, right? Yes, so it's deceptive. That's right. So his statement was basically you're trying to get to here, you want it to be 0, and as you give it a bigger number, it gets closer to 0, right? You give it 100, 1 over 100, give it 1,000, it's getting closer. It thinks it's getting closer and closer to 0, but it's actually getting farther away from just giving it 0 and it gets 0. 0 is the only input in which you hit target. So in that case, they call that a deceptive landscape. And these two guys, McMahon and Holcomb, they're working on solving those problems with an extended chaining approach. You can check out the reference in the paper there. So, but what I propose is not that. All that was to give you background, just so you know about evolutionary testing. Mine doesn't use source code, because in my life, I don't have source code, right? If I'm looking for a bug in Word or something like that, I don't have the source code for it. So, I'm talking about gray box evolutionary testing. In which case, we'll use, I'll explain it, we'll use the PID file from MyDataPro to set breakpoints on functions and stock bits and we'll talk about that. So that was all section 1. We're done with that. Now we're on section 2, which is how does the system actually go to work? It takes evolutionary testing and fuzzing, a previous tool I wrote called GPF, and leverages PyMan and Keystalker, and Python, and all that good stuff. And here's the system view. So on the lower left, you see, let's take a look. Turn my head to the right, that's better. I gotta look this way. So GPF is written in C, and that's got the guts, the evolutionary guts is right there. And then you see the target process is being stalked by the debugger, Python, and that's all the Python code. They both store everything in a MySQL database, and you can do the reports along with some PHP scripts from that. So the simple little protocol that they taught, GPFS, I call it the EFS GUI or the Pioneer bit or Keystalker or whatever you want to call it. It's all EFS is like the whole system, and then each bit, kind of has different names based on what it was on GPF or Pioneer, whatever. It says, are you ready? He says, yep, I'm ready, and he starts stalking the process, and then GPF communicates with the process, and then Pioneer stores the hit information. Okay, and so the stalking. I don't remember, I think I mentioned that later, but basically, a PID file, PID files, you know what that is? Everybody know what a PID file is? So you take the binary, you stick it into IDA Pro, and you run pin it down. Pin it down, basically, after IDA Pro, if it was able to successfully analyze the binary you want to stock, it gives it basically a list of all the functions and all the basic blocks. So you know what a function is? A basic block is like, when there's assembly, push, pop, jump, that's a basic block. Whenever there's a branch, those are the basic blocks. So you can have lists of breakpoints for all the functions and blocks. And it'll record all the either functions or basic blocks that were hit during the session that was played. That's going to be a big part of how fitness is calculated. You can choose which one to stop on, either functions or basic blocks. So, in the genetic algorithms, there's also something called genetic programming. It's basically a variable linked GA. It's not genetic programming because we're not trying to find snippets of code. We're working on data like a genetic algorithm does. And it's all custom code that I wrote. So basically the fitness function is how many functions or basic blocks can be hit, and also how diverse are the various sections, because we want to maintain a measure of diversity throughout. Okay, and I'll talk more about that. So here's my little corollary, again, academic kind of word, right? I don't know if that's even the right usage of corollary, but wanted to add just a few thoughts, basically, is what they are. Code coverage doesn't equal security necessarily, so if you get complete code coverage of the attack surface, it doesn't mean that you found all the bugs. But if you haven't got all the code coverage, then you've got even less security, right? So if you haven't tested, you haven't found the bugs. So that's just that makes sense. We know that. I talked about that last year on Fuzzy Talk at DEFCON. So basically, the best I know how to do is get 100% coverage of the attack surface if you can measure all the nodes on the attack surface and you know what it is, and you cover it all. That's good. Plus, if you have diverse session with fuzzy heuristics throughout, that's even better. So that's just sort of the best I know how to do. Okay, so how does the actual evolution work? We'll talk about the actual, basically, mating right now. So, but first I mentioned that it's an elitism pool, so that means the best session or pool. And I'll talk about the data structure in just a second. Gets carried over to the next generation automatically. That's called elitism of one. So one automatically gets carried over. You never lose the best to the next generation. So then we have session crossover, session mutation, pool crossover, pool mutation. We'll talk about them right after I explain the data structure. So the data is laid out such that you can have multiple pools. The idea with multiple pools is that it helps maintain diversity, which helps maintain attack surface coverage, which helps you find more bugs. So the smallest bit of data is called a token, and you can kind of see that this is, it was developed a while ago with network type protocols in mind, so like reads and writes and stuff, but it can be extended.